Hello everyone, this is Professor Keen. We have been talking about the law of the lever, and in my last lecture I provided an intuitive understanding of where Galileo is going with his geometrical proof of the law of the lever. Remember what the law of the lever is. It states that if you have a teeter-totter or a lever with a fulcrum, then when you apply forces to the two ends at potentially different distances from the fulcrum, those forces produce torques that are in equilibrium provided the ratio of the two forces goes as the inverse ratio of the lengths or the distances from the point that you're applying the force to the fulcrum. Okay, so I've drawn a picture here that corresponds to the way Galileo understands this. So you see here there is a string hanging down, and from that string at point C there is a support beam. And it's that point C is midway in this in the middle of the support beam, and then suspended from that support beam is a prism, some heavy prism that you have cut vertically at point D. So you have one block of length AD hanging from the left-hand side, and another block of length DB hanging from the right-hand side. And the support points are point L for the left block, where it's hanging from point G. And I forgot to label this, but point M right here is the support point for the right-hand block where it's hanging from point F. And what the law of the lever is going to claim is that the weights of these blocks, this weight is to this weight, in the same ratio as this distance, that is distance CF, is to this distance GC. In other words, the weight of block AD is to the weight of block DB in the same ratio, or the inverse ratio of those distances. So this block's weight is to that block's weight as the length CF, that length CF is to the length GC. Okay, so this is the claim, and this is equivalent to the law of the lever. All right, so this is what we're going to try to demonstrate geometrically. We did this intuitively in our last lecture, and we're going to do this mathematically now in this lecture. I know some of you are into geometrical proofs and some of you may not be, but I ask that you would just bear with this. And this is, I think you'll find this to be a well-argued proof if you have the endurance to look through it. Okay, so first of all, I want to say one other thing about this weight and this weight. So provided that this beam is made of a uniform material, the ratio of this weight is to the ratio of this weight in the same ratio as the length of this beam is to the length of this beam. So in other words, I can replace this side with the length AD to the length DB. And that is as CF is to GC. So this is an equivalent claim. Equivalent claim so long as the material is uniform. The thickness, I guess, and the direction going in and out of the page is the same. So as the material and the thickness of the beam is uniform. So what we want to prove here is this. This is our goal, what we're going to try to prove. That's our target. How do we prove this? Well, let's go through the proof as Galileo does it. You have to be a little bit patient here. Okay, so first of all, I'm going to number these so they're easy to refer to. So point 1 is that the distance CI is going to be 1/2 of the distance HI. So CI is 1/2 of HI. That just amounts to the claim that this string is halfway from end I and from end H. Okay, so this is the string C. String C is at midpoint of the bar. Okay, that's point 1. Point 2 is that GE is equal to 1/2 of EH. Okay, so again, this right here is 1/2 of EH. So you're claiming that this point right here, the suspension point, is halfway between points A and D, or between E and H. Okay, so that this block right here doesn't rotate. Okay, so this is the claim that the left block, left prism, is hangs in equilibrium. So it doesn't rotate, right? So this follows from our axiom that if you hang this, so if these weights are equal, the weight on this side and this side are equal, then this whole block will be in equilibrium about this point. Okay? So we're going to assume that to be true. Third thing is that we're going to say that EF is equal to 1/2 of EI. Okay, again, this is 1/2 of this whole distance. That is, this suspension point is right in the middle of this block. So the right prism is likewise hangs in equilibrium. Okay? And that's equilibrium about this point right here, and this one about this point right here. Okay, point 4 is that Fi is equal to Fe. That is, this right here and this right here are equal to one another. Okay? So this is essentially the same thing as this point 3 right here. I guess that's maybe redundant. Okay? Point 5 is HE is equal to AD. So this right here, this length right here, is equal to this length right here. So in other words, this point is right below there, and D is right below E. And likewise, point 6 is that EI is equal to DB. So this length right here is equal to this length right here. So this point is right above the cut point, and B is right below the end of that beam. Okay, so those are some of the things that we're going to be using. Okay. Now, let's go through the steps of this proof in some detail. So we can see right away, first of all, that the distance GE, oops, my tablet froze up. Let me give it a second to unfreeze, and we'll continue. Okay, GE plus EF. If you don't mind, I'm going to quit writing these bars over it because it's going to become a hassle. GE plus EF, all these are just distances, right, is equal to 1/2 of EH plus 1/2 of EI. What are we saying? That's GE and EF is 1/2 HE and EI. What we're saying, this follows from points 2 and 3. Okay? Because GE and EF, so GE plus EF, if you add these two together and you add these two together, they still have to be equal to one another. Okay? So we're basically adding equation 2 to equation 3. Step 2 is that GF is equal to 1/2 of HI. And this is because this follows, so GE and EF is just the same thing as GF. So if you take GE and EF, that's just the whole segment GF. And likewise, EH and EI, that's EH and EI, gives you HI, that whole distance right there, right? So 1/2 EH and 1/2 EI is going to be 1/2 the whole distance HI. So, good. Number 3, we can see that GF must then be equal to CI. This follows from the previous step 2, and 0.1. Okay, so this right here, if you take this to be the case, well, 1/2 hi by 0.1 is just ci. So we can go from here like that. Okay, so it follows from the previous step and invokes 0.1. Okay, so that basically, going back over here, we're saying that this distance gf we've just found is equal in distance to that distance ci right there. Okay, and now we're going to subtract the distance cf from both sides of equation 3. So we take gf, that is this distance right here, and subtract off this distance right here, gf minus cf, and that has to be equal to ci minus cf. Basically subtracting cf from both sides of equation 3. Okay, so we're saying that if you take this length and you subtract this length, you're left with this length. And likewise, if you take ci, that length, and you subtract cf, you're left with fi right there. Okay, so then we have gf take away cf, and as I guess this is what we were saying in the previous statement, that this distance gc is equal to fi. So gf take away cf, gf take away cf, you're left with gc, and ci, you take away cf, you're left with fi. So from previous step. Okay, remember this, it's sometimes easy to lose where we're going. We're trying to prove this ratio right here. I always found geometrical proofs a little bit challenging because you're trying to prove something and you're just doing these manipulations one from the other, but how do you know we're going toward this? That's why it's good to think about overall intuitively what we're trying to accomplish before you jump into these steps. Okay, point C, now we can say that GC is equal to FE. How do we know this? This is from the previous step, from step 5, and Roman numeral 4 up here, which says that Fi is just equal to Fe. So we've replaced Fi with Fe. So again, we're saying that this distance GC here happens to be equal to this distance EF. Okay. And now we're going to add CE to both sides. GC plus CE is equal to FE plus CE. So that's adding CE to both sides of equation 6. And now you can probably see that GC and CE is just going to give you the whole distance GE, right? So if you take these two, you add those together, that gives you GE, and FE plus CE, that's this right here plus this right here, that gives you CF, right? So there you have CF. So those two added together gives you those quantities, all right? And now, point 9. Now we're going to compare GE. GE is to EF. This is kind of like a ratio. This is how Galileo writes it. GE is to EF in the same ratio as CF is to GC. How do we know that this is the case? So this compared to this is the same as this compared to this. This follows from the previous step, that is from 8, and also step 6. Okay, so you take GE and divide it by FE or EF, and that's the same thing as taking CF and dividing by GC. So you're really combining 6 and 8. Okay, and what we're doing here is we're saying this length GE is to that length EF in the same ratio as CF is to GC. All right, number 10. Now notice this is a side point, but GE is to EF. It's also equal to the ratio of HE to EI. Where does this follow from? This follows from points 2 and 3 up here. GE is to EF, and so if you form the ratio of these two, it's the same as the ratio of EH is to EI, or HE is to EI. Okay, so we've just found two different expressions for the ratio GE to EF. Okay, so now point 11, hope we can fit this in, we have two more points to make, 11, so that means that HE is to EI in the same ratio as AD oops, let me go back, that was written kind of funny, as AD is to DB. How do we know that? This follows from 5 and 6, Roman numerals 5 and 6. So right here, HE is to EI in the same ratio as AD is to DB. Okay. And finally, point 12 now, this is where we bring all three of these 9, 10, and 11 together to say that GC is to CF in the same ratio as BD is to DA. Okay, so we're taking this is to, so we're starting with this right here, it's equal to that, but that is equal to that, and that is equal to that. So we're putting all three of these together. So this is from 9, 10, and 11 to get this right here. And notice that this is exactly what we're trying to prove right here. So thus, we know, so AD and DA are the same thing. So AD, we're going to invert both sides of this equation. AD is to DB. So inverting this side and inverting this side is in the same ratio as CF is to GC. And that is exactly what we're trying to prove, because AD is related to the weight of this side, and DB is the weight of this side, and CF is the length, the distance to which you're applying this force that's caused by the weight of DB, and GC is the length right here, that's the distance to the force of that's being applied by block AD. So this is exactly what we were to have demonstrated, as they say in a math class, that knows Latin, QED. Okay, and so there we have it. We have demonstrated geometrically the law of the lever. Therefore, the ratio of these two lengths is equal to the inverse of the ratio of the weights you're suspending them from. It's worthwhile just thinking about, this is a lot of work to go through a proof like this, but notice what we've accomplished. We've started simply with the axiom that equal weights at equal distances from a fulcrum are in equilibrium with one another, and then we have proceeded entirely deductively using geometry to demonstrate the law of the lever follows from that simple axiom. This is precisely what Galileo argues, and he bases this on the argument that Archimedes had provided almost 2,000 years before that. We'll stop there.